Welcome everyone, and welcome to the AluVET Vocational Training and Education for the Aluminium sector. This training is co-funded by the Erasmus programme of the European Union. I am Jan Lukaszewski, the Technical Manager of the Aluminium Federation in the United Kingdom. The Introduction to Metals series of modules explains the simple theory of metals and of metallurgy to enable students in subsequent modules to understand aluminium, its alloys, how aluminium is heat treated, and how it is rolled, extruded, and or welded. And in this module, we shall be looking at the effects of thermal expansion of aluminium. This project is funded with the support of the European Union. This publication reflects only the views of myself and the Aluminium Federation, and the Commission cannot be held responsible for the use which may be made of the information contained therein. The aim of this module is to understand the mechanism of thermal expansion and the dimensional response of aluminium to temperature. Having completed this module, you'll be able to calculate thermal expansion and contraction and understand the thermal expansion and contraction behavior and their effects. The knowledge of thermal expansion and its effects is essential to designing and understanding hot working processes such as hot rolling, extrusion, and welding. The ability to calculate thermal expansion will enable dimensional control during hot rolling of extrusion. And the ability to calculate and understand thermal expansion and or contraction is paramount to predicting the performance of products in service, that is aluminium in the environment. So let's start by understanding what thermal expansion is. Metals are held together by the metallic bond. When a metal is heated, the energy of its atoms increases. This causes the electron orbits to increasing the spacing of the electrons from the nucleus, effectively increasing the orbital diameter and effectively increasing the size of the atoms. The larger electron orbit diameters force a greater separation between the atoms, so metals expand. By putting energy into a metal, we excite the electrons. The electrons expand their orbits, increase the separation between atoms, and as atoms push apart, metals expand. Increasing the temperature increases the separation between atoms, expanding the metal. Now, increasing the temperature decreases the attraction between the negative electrons and the positive protons, so it actually decreases the strength of the metallic bond. So whilst it increasing temperature expands the metal, but it also reduces the strength of the metallic bond. So it reduces the strength of metals and the force that we require to work them. So at higher temperatures, to change the shape and metals, to change the shape and reshape metals, the force required is reduced. Now, conversely, decreasing the temperature reduces the diameter of the atomic orbits. so the space in between atoms. So as metals contract and shrink, they increases the strength of the metallic bond. Effectively, by putting energy into metals, we expand the atoms, the metals expanding, so expand. Now, so let's understand what thermal expansion is. Thermal expansion of a metal is the reversible dimensional change resulting solely from a change in temperature. Now, the equation for calculating change in original length on heating or cooling is the coefficient of expansion times the original length times the change in temperature. I shall explain coefficient of expansion shortly. Now, cooling will result in a negative change, a shrinking. Heating is a positive change, so an expansion, growth. Now, the coefficient of expansion is the factor, it's the multiplication factor that we use to calculate expansion or contraction of aluminium with temperature. Now, in reality, the coefficient of aluminium is not a constant. Coefficient of expansion of aluminium is not a constant, but it does increase almost linearly with temperature. So you can see in the graph, as aluminium gets hotter, the coefficient of thermal expansion, the factor that we multiply expansion by, increases. Now that means that the rate of expansion of aluminium increases with increasing temperature. In other words, the rate aluminium expands actually increases with increasing temperature. So the coefficient of expansion is not a constant. Now here we have a problem because textbooks normally state a single value for the coefficient of expansion. And what they actually do is state an average value over a defined temperature range, typically 20 to 100 degrees C. Remembering our hot working temperatures will be 300 to 400 degrees C. Now with aluminium, we're very, very fortunate in that the rate of linear, its coefficient of expansion is almost a linear arrangement. So we can predict how aluminium is going to expand. But the increase in change in coefficient of expansion of aluminium means that it actually expands more with increase in temperature. So this is important to understand during hot rolling and extrusion. Now, different alloying elements affect the thermal expansion and contraction of the different aluminium alloys. Additions of alloying elements such as copper, iron, magnesium, nickel, silicon, or zinc to aluminium change the expansion coefficient, and they change it in a linear manner. So we're very, very important, very fortunate in the aluminium coefficient of thermal expansion is almost linear, and the alloying effects are almost linear. So magnesium or zinc, and magnesium and zinc are the two top lines on the graph, increase the rate of expansion, whereas other additions decrease it. If you look at silicon, middle long line at the bottom, the increasing rate of silicon reduces the coefficient of aluminium. Now, this means that each aluminium alloy and each series of aluminium alloys will have different rate of expansions. We cannot use a single coefficient of expansion across aluminium per se. Now, each aluminium series and its suballoys have different rates of expansion. Now, you will note in the table here that The table gives an average value over a temperature range of 20 to 100 degrees Celsius. And most textbooks only give coefficient values up to 100 degrees C, remembering that hot working temperatures, extrusion temperatures, are going to be 300 to 400 degrees C, and welding temperatures will be much, much higher. So let's have a look how we calculate thermal expansion. So the formula for calculating thermal expansion is the original length in millimeters times the temperature change times the coefficient of expansion. And in this example, we're starting off with 2905 millimeters, and we're going to increase the temperature by 20 degrees C. The coefficient of expansion is 23.5 times 10 to the minus 6. So when you do the maths, an approximately 3 meter length of aluminium increasing by 20 millimeters by 20 degrees C temperature will grow by 1.35 millimeters, a significant amount. Now, increasing temperature increases the separation of atoms, expanding the metals. An increase in temperature decreases the attraction between the negative electrons and the positive protons, so it decreases the strength of the metallic bond. Now that means that increasing temperature expands the metals, but also reduces the strength of the metallic bond. Now that means that the strength of aluminium with increase in temperature, yield and tensile strength reduces significantly at elevated temperatures. And you can see the fall off in the graph. Typically, by the time we're at temperatures of 350 degrees C, we've reduced the tensile strength of aluminium by about 80%. So at elevated temperatures, aluminium strength is significantly reduced and it becomes extremely ductile. Now that means that hot working temperatures enable high reductions and change in shape of aluminium without failure. So heating aluminium to elevated temperatures reduces its strength, makes it super plastic, which makes it infinitely perfect for hot working, extrusion and hot rolling. Now, because dimensional changes result from thermal expansion, and at elevated temperatures, the yield and tensile strength fall off. So at elevated temperatures, the tensile strength, the yield and tensile strength of aluminium is significantly reduced, but conversely, it is significantly expanding. If we constrain the aluminium, such as in a corrugated roof, there are situations where the expansion overcomes the tensile strength of the aluminium, yield strength of aluminium, and we see buckling. I trust you've understood the importance of thermal expansion and its effect on mechanical properties. Here's some further reading. Thank you very much.